The complete and comprehensive history of Linux, from inception to global dominance, cannot be told without understanding Unix, its philosophical ancestor and technical inspiration. In the 1960s, computing was dominated by massive mainframe systems that cost millions of dollars and required specialized facilities. Time-sharing systems, which allowed multiple users to interact with a computer simultaneously, represented cutting-edge technology. In 1964, Massachusetts Institute of Technology, Bell Labs, part of AT&T, and General Electric began collaborating on an ambitious project called Multics, Multiplexed Information and Computing Service. Multics aimed to create a comprehensive time-sharing system with unprecedented capabilities, including security features, file systems, and support for numerous simultaneous users. The project was technically innovative, but became increasingly complex and expensive. By 1969, Bell Labs withdrew from the Multics project, concluding it had become too ambitious and unwieldy. However, two Bell Labs researchers, Ken Thompson and Dennis Ritchie, had been deeply involved in Multics and appreciated its goals, even if they questioned its execution. Thompson, in particular, wanted to continue experimenting with operating system concepts. In the summer of 1969, while his wife was away on vacation, Ken Thompson found himself with access to an idle DEC PDP-7 minicomputer. This machine, obsolete even then, provided Thompson with an opportunity to implement his ideas. Working intensively, he created a simple operating system with a hierarchical file system, a command line interpreter, shell, and some utility programs. The entire system could be developed by one person in a matter of weeks, a stark contrast to Multics's complexity. Brian Kernighan, another Bell Labs researcher, suggested the name Unix as a pun on Multics. Where Multics was multiplexed and complex, Unix was uniplexed and simple. The name stuck, though its spelling later changed from Unix to Unix. Initially written in assembly language for the PDP-7, Unix was later rewritten for the DEC PDP-11, a more capable machine. Dennis Ritchie had been developing the C programming language, evolving it from earlier languages like B and BCPL. In 1973, Ritchie and Thompson made the revolutionary decision to rewrite Unix in C. This decision transformed Unix from a machine-specific system into a portable operating system. While writing an operating system in a high-level language was unusual and initially controversial, some believed it would be too slow. The benefits proved enormous. Unix could now be ported to different hardware platforms with relatively modest effort. Most of the code could be reused. Only machine-specific parts needed rewriting. The C language itself was elegant and powerful, providing low-level hardware access while remaining more abstract than assembly language. C became inseparable from Unix, and both spread together through the computing world. Unix embodied several design principles that would profoundly influence computing. Simplicity. Unix tools should do one thing well. Rather than creating monolithic programs with many features, Unix favored small, focused utilities. Composability. Programs should work together. Unix introduced the concept of pipes, allowing one program's output to become another's input, enabling users to combine simple tools into powerful workflows. Text-based interfaces. Unix used plain text for data and configuration, making systems transparent and manipulable with standard tools. Hierarchical file system. Everything in Unix is treated as a file, including devices and interprocess communication mechanisms. This unified abstraction simplified system design. Modularity. The system was divided into clearly separated components: the kernel, managing hardware and resources; the shell, interpreting user commands and utilities, performing specific tasks. These principles created a flexible, powerful system that programmers loved. Unix encouraged experimentation and allowed users to customize their environment extensively. AT&T, operating as a regulated monopoly, was restricted from entering the computer business directly. Consequently, Bell Labs licensed Unix to universities at nominal cost, providing source code for educational purposes. This decision had far-reaching consequences. The University of California, Berkeley, became a major center for Unix development. Graduate student Bill Joy created improvements, including the VI text editor and the C shell. Berkeley released its own Unix distribution called BSD, Berkeley Software Distribution, in 1977, initially as add-ons to AT&T's Unix. Berkeley's Computer Systems Research Group, funded partly by DARPA, Defense Advanced Research Projects Agency, made fundamental contributions to Unix. BSD Unix introduced the TCP/IP networking protocols that would become the Internet's foundation. Virtual memory improvements, job control, and many other innovations originated from Berkeley. The BSD distributions, including 4.1 BSD, 4.2 BSD, 4.3 BSD, and later 4.4 BSD, became immensely influential. Many commercial Unix systems incorporated BSD code, the BSD license permissive and allowing proprietary derivatives, contrasted with later copyleft licenses. As Unix's popularity grew, commercial vendors recognized its potential. Companies created proprietary Unix versions, each with unique features and incompatibilities. Sun Microsystems developed Sun OS, later Solaris. IBM created AIX. Hewlett-Packard offered HPUX, and numerous other vendors produced their own variants. AT&T, after divestiture in 1984, aggressively pursued Unix commercialization through Unix System V. The company attempted to standardize Unix while controlling its direction, creating tension with other vendors and the BSD community. The Unix wars of the late 1980s and early 1990s saw competing standards, incompatible implementations, and legal disputes. The Open Software Foundation formed to counter AT&T's control, while Unix International supported AT&T. This fragmentation frustrated users and developers who wanted a consistent platform. Additionally, Unix systems were expensive. Commercial Unix licenses cost thousands of dollars, and the hardware required to run Unix workstations and servers cost tens of thousands to millions of dollars. Unix remained primarily in academic, research, and corporate environments, inaccessible to most individuals. Richard Matthew Stallman, a programmer at MIT's Artificial Intelligence Laboratory, became increasingly frustrated with proprietary software's restrictions during the early 1980s. The AI lab had a culture of sharing code and modifying software, but proprietary software licenses prevented this cooperation. A specific incident crystallized Stallman's concerns. The lab received a laser printer that frequently jammed. Previously, Stallman had modified printer software to notify users of jams, but the new printer came with proprietary software he couldn't modify. This inability to solve a simple problem through software modification epitomized proprietary software's limitations. In September 1983, Stallman announced the GNU project, a recursive acronym, GNU's Not Unix, aiming to create a completely free Unix-like operating system. Free meant freedom, not necessarily zero cost. Users should have the freedom to run, study, modify, and distribute software. In 1985, Stallman published the GNU Manifesto, articulating his vision for free software. He founded the Free Software Foundation, FSF, to support the GNU project financially and legally. Stallman personally wrote several crucial components. GNU Emacs, a powerful extensible text editor that became enormously popular. GCC, GNU Compiler Collection. Initially the GNU C compiler, later supporting multiple languages. GCC became the standard compiler for Unix-like systems. GDB, GNU Debugger, a comprehensive debugging tool. Beyond code, Stallman created legal infrastructure for free software. The GNU General Public License, GPL, first released in 1989, version 1, and revised in 1991, version 2, established copyleft, using copyright law to ensure software remained free. Anyone could modify and distribute GPL software, but derivatives must also be released under the GPL. This prevented companies from taking free software, modifying it, and releasing proprietary versions. By the late 1980s, the GNU project had created most components needed for a complete operating system: editors, compilers, debuggers, shells, and utilities. However, one critical component remained incomplete: the kernel. The GNU project began developing a kernel called GNU Hurd in 1990. Herd used a microkernel architecture where most operating system services ran as user space processes rather than in the kernel itself. This architecture promised better modularity and stability. However, Herd's development proved far more difficult than anticipated. Microkernel design was complex, and the project made slow progress. By 1991, no working Herd kernel existed, and completion seemed years away. This created a paradox. The free software movement had created excellent tools, but lacked a free kernel to run them on. Developers either used proprietary Unix systems or Minix, a minimal Unix-like system created by Andrew Tannenbaum for teaching operating system concepts. Minix was inexpensive and came with source code, but Tannenbaum deliberately kept it simple and restricted modifications to maintain its educational clarity. The stage was set for Linux's emergence. A confluence of available tools from GNU demonstrated need, free Unix kernel, enabling technology, increasingly powerful personal computers, and communication infrastructure, the growing internet. Linus Benedict Torvalds was born on December 28, 1969, in Helsinki, Finland. His family had academic inclinations. Both parents were journalists, and his grandfather was a statistician and poet. Torvalds showed early interest in computers, programming on his grandfather's Commodore VISC-20 in the early 1980s. In 1988, Torvalds enrolled at the University of Helsinki to study computer science. The university's computer science program was rigorous, emphasizing both theoretical foundations and practical programming. Torvalds excelled, though he described himself as lazy, motivated to solve problems primarily when they interested him personally. In 1990, Torvalds took a course on Unix and C programming. The course used Minix, Andrew Tannenbaum's educational Unix-like operating system. Minix ran on PC-compatible computers with Intel 80286 or 80386 processors, making Unix-like operating systems accessible to students. Tannenbaum, a respected computer science professor, created Minix to teach operating system concepts. His textbook, Operating Systems Design and Implementation, included complete Minix source code. However, Tannenbaum intentionally kept Minix simple and restricted modifications. He wanted Minix to remain a clear educational example, not to evolve into a production system. In early 1991, Torvalds purchased a new PC with an Intel 80386 processor, 4 MB of RAM, and a 40 MB hard drive. Substantial for the time, but expensive, costing about $3,500. The 386 processor was significantly more powerful than the 286, with 32-bit architecture, virtual memory support, and protected mode operation. Torvalds installed Minix on his new computer and began exploring the 386's capabilities. He was particularly interested in task switching, the ability to run multiple processes that appeared to execute simultaneously. The 386's protected mode and task switching features fascinated him. Torvalds' initial goal was modest: create a terminal emulator to access the university's Unix systems remotely. The university had a dial-up service, but Torvalds wanted to write his own terminal program to understand the 386's task-switching capabilities. He began programming in assembly language, directly manipulating the 386's hardware features. The terminal emulator needed to handle keyboard input while simultaneously managing serial port communication, a perfect task-switching exercise. As Torvalds developed his terminal emulator, he needed additional functionality. He implemented basic file I/O to save and load data. The file I/O required interacting with the hard disk. To test and debug, he needed to boot his code directly rather than running under Minix. Gradually, almost accidentally, Torvalds was implementing kernel functionality. He added support for multiple processes, memory management, and basic file system operations. The project evolved from a terminal emulator into a primitive operating system kernel. Torvalds wrote the kernel from scratch, not copying code from Minix or other systems. He designed it as a monolithic kernel, different from Minix's microkernel structure, where most operating system services run in kernel mode with direct hardware access. While less theoretically elegant than microkernels, monolithic kernels offered better performance. By August 1991, Torvalds had something working. On August 25, 1991, he posted a message to the comp.os Minix newsgroup that would become historic. Hello everybody out there using Minix. I'm doing a free operating system, just a hobby. Won't be big and professional like GNU. For 386,486, 8 clones. This has been brewing since April and is starting to get ready. I'd like any feedback on things people like, Josh's dislike in Minix, as my OS resembles it somewhat. Same physical layout of the file system due to practical reasons. Among other things, I've currently ported Bash 1.08 and GCC 1.40, and things seem to work. This implies that I'll get something practical within a few months, and I'd like to know what features most people would want. Any suggestions are welcome, but I won't promise I'll implement them. Linus, Torvalds Akruna.Helsinki.fi. P.S. Yes, it's free of any Minix code, and it has a multi-threaded FS. It is not portable, uses 386 task switching, etc. And it probably never will support anything other than AT hard disks, as that's all I have. This modest announcement contains several notable elements. Torvalds characterized his project as just a hobby and explicitly said it wouldn't be big and professional. He mentioned porting Bash and GCC GNU tools, demonstrating the project's reliance on GNU components. He emphasized the kernel was free of any Minix code, important both legally and philosophically. And he incorrectly predicted it probably never will support anything other than AT hard disks and wouldn't be portable. Linux would eventually run on more hardware platforms than any other operating system. On September 17, 1991, Torvalds made version 0.101 available for download. This wasn't a public announcement. Only people following the newsgroup discussions knew about it. The release included the kernel source code, about 1,000 lines, plus minimal documentation. Version 0.001 was barely functional. It required Minix to compile and couldn't run independently. Users needed Minix installed to build the kernel and create a file system. The kernel could run Bash and GCC, but little else. No device drivers existed beyond keyboard and hard disk support. Networking, graphics, and most hardware weren't supported. Despite these limitations, version 0.E1 demonstrated that a single motivated individual could create a working kernel. The source code was comprehensible, and interested programmers could study and modify it. Version 0.02, released in October 1991, was the first version Torvalds publicly announced. It could execute basic Unix commands and run Bash and GCC. Torvalds initially released it under a restrictive license prohibiting commercial distribution, concerned about exploitation but wanting to share his work. Early adopters were primarily Minix users frustrated with Minix's limitations. They saw Linux as a more flexible alternative where they could contribute improvements. The comp.os Minix newsgroup became an active discussion forum for Linux development. Ari Lemke, Torvalds' colleague at Helsinki University, gave the project its name. Torvalds had initially called it Freaks, combining free, freak, and X for Unix, but Lemke preferred Linux, combining Linus and Unix, and named the FTP directory accordingly. The name stuck, though pronunciation debates continue. Torvalds himself says Linux. In January 1992, Torvalds made a crucial decision. He relicensed Linux under the GNU General Public License version 2. This decision profoundly shaped Linux's development and success. Several factors influenced this choice. Torvalds believed in free software principles and wanted Linux freely available. The GPL was already well established and legally sound. Most importantly, relicensing under GPL made Linux compatible with GNU tools, enabling anyone to create a complete free operating system. The GPL's copyleft provision meant improvements to Linux had to be shared. Companies couldn't take Linux, modify it privately, and release proprietary versions. This requirement ensured contributions would benefit everyone, encouraging collaboration. Years later, Torvalds acknowledged this was one of his best decisions. The GPL aligned Linux with the free software movement and enabled the collaborative development that made Linux successful. Linux attracted developers quickly, Programmers worldwide contributed patches, adding features and fixing bugs. Communication happened through news groups and mailing lists. The internet was young, but email and Usenet provided global connectivity. Contributors came from diverse backgrounds. Some were students learning operating systems. Others were professional programmers frustrated with proprietary Unix limitations. Hobbyists enjoyed exploring the 386's capabilities. This diversity brought different perspectives and expertise. Torvalds managed development by reviewing patches and deciding what to accept. This benevolent dictator model, where one person has final authority but listens to community input, proved effective. Torvalds had strong technical judgment and usually made good decisions about what code to accept. The development pace was extraordinary. New versions appeared every few weeks, each adding features and hardware support. By the end of 1991, Linux was becoming genuinely useful, no longer just an academic exercise. In early 1992, Orest Zborowski ported the X Windows system to Linux. This milestone was crucial. X provided graphical user interfaces for Unix systems, and its availability on Linux made the system practical for desktop use, not just servers and development machines. X originated at MIT in the 1980s as a network-transparent windowing system. It followed the client-server model where applications, X clients, communicated with a display server, X server, that managed screen, keyboard, and mouse. X's network transparency allowed applications to run on one machine while displaying on another. The export required substantial work. X needed proper hardware support for graphics cards, more sophisticated memory management than early Linux provided, and various kernel features not yet implemented. Zborowski's work demonstrated Linux's growing maturity. With X available, desktop environments could be developed. Early window managers like TWM and FVWM provided basic graphical environments. These weren't as sophisticated as commercial Unix desktop environments or Windows, but they made Linux accessible to users uncomfortable with command line interfaces. Installing early Linux was complex. Users needed to download kernel sources, compile them, create file systems, install GNU tools individually, and configure everything manually. This process required substantial technical knowledge and deterred many potential users. The concept of a Linux distribution solved this problem. A distribution packages the Linux kernel with necessary software, installation tools, and documentation, making installation and configuration much easier. H.J. Liu's Bootroot, one of the earliest distributions providing a minimal bootable Linux system. It demonstrated that Linux could be packaged for easier installation. Soft Landing Linux System, SLS, created by Peter MacDonald in 1992, SLS provided a more comprehensive system including X Windows. However, it gained a reputation for instability and packaging problems. Slackware, released by Patrick Volkerding in July 1993, Slackware emphasized simplicity and Unix-like configuration. It used simple package management, tar archives with installation scripts, and provided a stable minimalist system. Slackware survives today as the oldest continuously maintained distribution. Debian. Ian Murdoch founded the Debian project in August 1993. Debian distinguished itself through commitment to free software principles, community governance, and technical excellence. The Debian Social Contract and Debian Free Software Guidelines established principles that guided development. Debian introduced sophisticated package management through DPKG and later APT, Advanced Package Tool, simplifying software installation and dependency resolution. Distributions dramatically lowered barriers to Linux adoption. Users could install complete systems in hours rather than days or weeks. This accessibility expanded Linux's user base beyond kernel developers to system administrators, researchers, and enthusiasts. Linux's hardware support expanded rapidly. Developers contributed drivers for various devices, network cards, SCSI controllers, sound cards, printers, and more. The community's diversity meant someone usually owned any given hardware and was motivated to make it work. However, hardware support was uneven. Some vendors provided documentation enabling driver development, while others treated hardware specifications as proprietary secrets. Linux hardware support was best for devices with available documentation or reverse engineering efforts. The community developed strategies for handling hardware support challenges. Public pressure sometimes convinced vendors to release specifications. Reverse engineering allowed driver development despite vendor non-cooperation, and growing Linux popularity eventually made it commercially important enough that vendors supported it directly. As Linux grew, documentation became crucial. The Linux Documentation Project, LDP, founded in 1992 by Matt Welsh, coordinated documentation efforts. Volunteers wrote how-tos, documents explaining how to accomplish specific tasks, guides, and manuals. Matt Welsh also wrote Linux Installation and Getting Started, the first comprehensive Linux book released freely online. This documentation was invaluable for new users navigating Linux's complexity. Mailing lists proliferated, each focusing on specific aspects: kernel development, particular distributions, hardware support, etc. These lists became repositories of knowledge, with archives providing searchable solutions to common problems. Linux user groups, LUGs, formed in many cities, providing local community and support. LUGs held meetings, install fests, helping people install Linux and presentations. They created social networks that sustained Linux adoption. By 1993, about 100 developers regularly contributed to the kernel. Torvalds remained the central coordinator, but development was genuinely collaborative. Significant features emerged: TCP/IP networking, essential for internet connectivity. Networking support made Linux viable for servers. Virtual memory improvements. Better memory management enabled more sophisticated applications. File system development. Beyond the original XT file system, XT2 provided better performance and reliability. Support for other file systems. FAT. ISO 9662 for CD-ROMs. Improved compatibility. SMP support, early symmetric multiprocessing support, allowed Linux to utilize multiple processors, though full SMP maturity came later. The kernel grew substantially. By 1994, it contained hundreds of thousands of lines of code, yet it remained comprehensible to dedicated programmers, and the community successfully integrated contributions from many sources. Linux 1.0, released in March 1994, marked Linux's transition from experimental project to serious operating system. With about 176,000 lines of code, version 1.0 included stable kernel API for device drivers and modules, comprehensive networking support, TCP/IP, virtual memory with demand paging and swapping, multiple file system support, POSIX compliance for Unix compatibility, loadable kernel modules, support for various hardware architectures. Though x86 dominated, version 1.0 was reliable enough for production use. Organizations began deploying Linux for real workloads, not just experimentation. The release generated significant publicity, with technology publications covering Linux's progress. Torvalds and other core developers celebrated with a party at the University of Helsinki. The achievement was remarkable. In less than 3 years, a student hobby project had become a sophisticated operating system challenging commercial Unix systems. By 1994, commercial interest in Linux was emerging. Bob Young's ACC Corporation distributed Linux on CD-ROM, addressing the challenge of downloading hundreds of megabytes over slow dial-up connections. CD-ROM distributions typically cost $40–50, a fraction of commercial Unix prices. Mark Ewing founded Red Hat Software, later Red Hat Inc., in 1994. Though the first official Red Hat Linux release came in 1995, Ewing saw opportunity in providing Linux with professional support, targeting businesses uncomfortable with community-only support. InfoMagic and Walnut Creek CD-ROM also distributed Linux, often compiling multiple distributions onto CD-ROM sets. These companies provided important distribution channels before broadband internet made large downloads practical. Linux began appearing in technology magazines. Linux Journal, founded in 1994, became the first publication dedicated to Linux. Mainstream computer magazines ran occasional articles, usually emphasizing Linux's technical nature and unsuitability for non-technical users, perceptions that would gradually change. Linux 1.2, released in March 1995, brought numerous improvements. The kernel had grown to about 310,000 lines of code. Key enhancements included better multiprocessing support, improved networking and network protocols, sound card support, PCMCIA support for laptops, additional file systems, many new device drivers. The 1.2 kernel demonstrated Linux's versatility. It ran on desktop computers, servers, and increasingly on laptops. While hardware support remained inconsistent, it was rapidly improving. Development methodology evolved. Torvalds implemented a version numbering scheme distinguishing stable and development kernels. Stable versions, even minor numbers, 1.0, 1.2, 2.0, etc., received primarily bug fixes. Development versions, odd minor numbers, 1.1, 1.3, 2.1, etc., incorporated new features and experimental code. This scheme balanced stability for users with innovation for developers. The Apache HTTP server project, started in 1995, became inseparable from Linux's success. Apache was created from the NCSA HTTPD web server, incorporating various patches, hence Apache Server. Apache quickly became the dominant web server software, and it ran primarily on Linux. The combination of Linux, Apache, MySQL, an open-source database, and PHP, C, Perl, Python programming languages became known as LAMP, the standard platform for web applications. This stack was entirely free, powerful, and well-suited for the web's growth. As the internet expanded explosively during the mid-1990s, Linux and Apache powered much of that growth. Startups building web services chose LAMP for its cost-effectiveness and flexibility. This practical success demonstrated Linux's value proposition beyond theoretical arguments about free software. Linux 2.0, released in June 1996, was a major milestone. With symmetric multiprocessing, SMP, support, Linux could effectively utilize multiple processors, positioning it for enterprise server use where SMP systems were common. Version 2.0 also introduced support for multiple processor architectures beyond x86, Alpha, Digital Equipment Corporation's 64-bit RISC processor, Spark, Sun Microsystems processor architecture, MIPS, used in various embedded systems and workstations, PowerPC, IBM's RISC architecture. This portability demonstrated Linux's clean design and active developer community. Porting to new architectures required substantial work, but Linux's modular structure and available source code made it feasible. The 2.0 kernel contained about 800,000 lines of code, reflecting Linux's growing sophistication. Memory management, networking, and file system performance all improved substantially. 1996 saw increasing corporate acknowledgement of Linux. While major software vendors still primarily targeted Windows and commercial Unix, some companies began supporting Linux. Netscape announced Linux support for its web browser and server products. Informix and Oracle, major database vendors, announced Linux versions, though Oracle's support was limited initially. Coral announced plans to port WordPerfect to Linux, recognizing demand for productivity applications. Computer manufacturers began offering Linux pre-installed on some systems, though this remained rare. Dell, Compaq, and others experimented with Linux systems, primarily targeting developers and technical users. The commercial endorsements were significant psychologically. They suggested Linux was transitioning from hobbyist project to legitimate business platform. However, Linux remained tiny compared to Windows and commercial Unix in market share and revenue. In 1997, Eric S.I. Raymond presented a paper at the Linux Congress titled The Cathedral and the Bazaar. This essay analyzed Linux's development model and became immensely influential. Raymond contrasted two development approaches: the Cathedral, traditional software development, where code is carefully crafted by a small group of developers working in isolation, releasing infrequently after extensive internal testing. Commercial software typically followed this model. The Bazaar, Linux's approach, where development happens openly with many contributors, frequent releases, and rapid feedback. Raymond's famous principle, given enough eyeballs, all bugs are shallow, later called Linus's law. Raymond argued the Bazaar model, while seemingly chaotic, produced better software through transparency, diverse perspectives, and rapid iteration. He documented how Linux's development contradicted conventional software engineering wisdom, yet succeeded spectacularly. The essay influenced both the open source movement and business thinking about software development. It provided theoretical framework for understanding why Linux worked, making it more comprehensible to skeptics. In 1997, Torvalds completed his master's degree at the University of Helsinki. His thesis, Linux, a Portable Operating System, described Linux's design and portability. The thesis wasn't groundbreaking theoretically. Linux's value was practical, not academic. But completing his degree while maintaining kernel development demonstrated Torvalds' discipline. Torvalds remained Linux's central figure, but was transitioning from programmer to manager. He still wrote code and reviewed patches. But increasingly, he coordinated others' work. This transition was necessary as Linux grew too large for one person to manage every detail. In January 1998, Netscape Communications made a stunning announcement. It would release the source code for its Netscape communicator browser. This decision, influenced partly by Linux's success, marked a turning point in open source software's business perception. Netscape faced challenges from Microsoft's Internet Explorer, which was free and integrated with Windows. Netscape executives, particularly Eric Hahn and CTO Mike Homer, believed open sourcing could rally developer support and create community momentum. Raymond's Cathedral and the Bazaar essay influenced this thinking. The announcement catalyzed discussions about free software's messaging. Richard Stallman's free software terminology confused people. Did free mean no cost or freedom? Business executives associated free with unprofessional or communist. In February 1998, a meeting in Palo Alto brought together open source leaders including Eric Raymond, Bruce Perens, Tim O'Reilly, and others. Christine Peterson proposed the term open source as more business-friendly than free software. The group founded the Open Source Initiative, OSI, to promote this framing. The distinction between free software and open source created philosophical tension. Stallman emphasized freedom and ethics. The open source movement emphasized practical benefits like better quality, security, and flexibility. This tension continues, though the movements substantially overlap. 1998 brought unprecedented corporate Linux support. Major technology companies announced Linux initiatives. IBM announced plans to support Linux across its product lines. This was extraordinary. IBM was a computing giant with its own Unix AIX, yet it embraced Linux. Bob Sampson, IBM's Linux chief, committed resources to Linux development. Oracle. Larry Ellison announced Oracle Database would officially support Linux. Oracle's support legitimized Linux for enterprise database workloads. Compaq announced enterprise-level Linux support and Linux-based servers. Dell began offering Linux pre-installed on select systems. Intel invested in Linux development, particularly optimizations for Intel processors. SAP, the enterprise software giant, announced Linux support for its applications. These endorsements weren't just marketing. Companies contributed code, funded development, hired Linux developers, and integrated Linux into product strategies. The corporate involvement accelerated Linux development while raising questions about control and direction. Red Hat exemplified the open source business model. Founded by Mark Ewing and Bob Young, Red Hat didn't charge for Linux itself. Anyone could download it freely, but monetized through support and services. Companies paid for technical support, training, and consulting. Enterprise Linux Red Hat, Enterprise Linux RHL, provided a stable supported platform with guaranteed update cycles and certification. Value-added tools, management tools, clustering software, and integration products. This model worked because while Linux was free, enterprise deployment required expertise. Companies willingly paid for support, documentation, and guaranteed stability. Red Hat's revenue grew rapidly, demonstrating open source could be commercially viable. Other companies pursued similar strategies. CUSE in Germany built a successful business around Linux. Turbo Linux targeted Asian markets. Mandrake Soft, later Mandriva, focused on desktop usability. Linux 2.2, released in January 1999, brought improvements crucial for enterprise use. Enhanced SMP support for up to 16 processors, improved networking performance and protocols, better memory management and scalability, enhanced file systems, Y2K compliance, important given Millennium fears, support for more hardware devices. The 2.2 kernel was stable and performant enough for demanding server workloads. Companies deployed Linux for web servers, file servers, and database servers. While not yet challenging Windows in desktop market share, Linux was gaining server market share from commercial Unix systems. The dot-com bubble's exuberance extended to Linux companies. In August 1999, Red Hat held its initial public offering. The stock, priced at $14, surged to $53.50 on the first trading day, giving Red Hat a market capitalization over $6 billion. This success, despite Red Hat not being profitable, demonstrated investor enthusiasm for open-source business models. VA Linux Systems, later VA Software, which manufactured Linux-based computer systems, went public in December 1999. The stock rose from $30 to $239.25 on the first day, a 698% gain, the largest first-day IPO gain in stock market history at that time. The company's market cap briefly exceeded $9 billion. Other Linux companies went public or received substantial venture capital: Caldera Systems, Turbo Linux, LinuxCare, and others. The valuations were astronomical relative to revenues, reflecting dot-com bubble dynamics more than rational assessment. These IPOs brought Linux mainstream attention. Business publications covered Linux extensively. The stock performance suggested Linux was revolutionary, though the valuations proved unsustainable when the bubble burst. Linux's success generated controversies. Microsoft, seeing Linux as a threat, launched the Get the Facts campaign comparing Windows favorably to Linux on cost and performance. Microsoft executives, particularly Steve Ballmer and Jim Allchin, publicly criticized Linux and open-source development. Some criticized Linux's technical decisions. The monolithic kernel architecture was debated. Was it inferior to microkernels? Andrew Tannenbaum, Minix's creator, famously declared Linux as obsolete in 1992, arguing microkernels were superior. Torvalds defended the monolithic approach, emphasizing performance and simplicity. Time vindicated Torvalds. Linux succeeded, while microkernel systems remained largely academic. The Linux community itself wasn't always harmonious. Debates erupted over technical decisions, development priorities, and philosophical questions. Should Linux prioritize desktop or server use? How should the kernel balance backward compatibility versus innovation? These debates sometimes turned contentious, with strong personalities clashing. Desktop Linux remained challenging. While server Linux thrived, desktop adoption lagged. Hardware support, particularly for laptops, was inconsistent. Software availability was limited. Many popular applications didn't run on Linux. The command line remained necessary for many tasks, deterring non-technical users. Multiple desktop environments, GNOME, KDE, fragmented effort rather than concentrating it. However, these challenges didn't diminish Linux's server success. By 2000, Linux was established as a serious server platform, and its trajectory pointed toward continued growth. The dot-com bubble burst in 2000-2001, devastating technology stocks. Linux companies weren't spared. VA Linux's stock, which peaked near $300, collapsed to under $2. Red Hat's stock fell from highs around $150 to under $5. Companies that had raised millions found themselves struggling as revenue expectations failed to materialize. VA Linux pivoted away from hardware to software, eventually becoming SourceForge Inc. and later GeekNet. LinuxCare, once valued highly, struggled and contracted. Turbo Linux and Caldera faced difficulties. The boom's euphoria gave way to retrenchment. However, Linux itself continued thriving despite financial market turmoil. The technology's value wasn't diminished by stock prices. Organizations continued adopting Linux because it worked well and saved money. The bubble's burst actually helped by resetting expectations and forcing sustainable business models. Linux 2.4, released in January 2001, represented major maturation, with improvements including support for up to 64 GB of RAM and 32 processors on 32-bit systems, better file system support, including ext3, journaling file system, improved USB support, better laptop support, including PCMCIA and power management, logical volume manager, LVM for flexible disk management, device mapper for advanced storage management, improved networking, including NetFilter e-tables for firewalling. The 2.4 kernel was stable and performant for demanding enterprise workloads. Companies deployed it for mission-critical applications with confidence. File system journaling particularly improved reliability. System crashes no longer required lengthy file system checks. IBM's support for Linux wasn't merely announcements. The company committed substantial resources. In 2001, IBM announced it would invest $1 billion in Linux development, marketing, and services. This investment included hundreds of developers working on Linux kernel and applications, porting IBM middleware and applications to Linux, marketing campaigns promoting Linux certification programs, research and development on Linux scalability and performance. IBM's motivations were strategic. The company competed against Sun Microsystems, HP, and others in Unix markets. Rather than developing a proprietary Unix, IBM embraced Linux as a common platform. Linux reduced development costs while providing a competitive advantage through superior support and services. IBM contributed significant code to the kernel, particularly for scalability on large systems. The company helped port Linux to its mainframe systems, System Z, enabling Linux to run on the most powerful computers IBM manufactured. Mainframe Linux was initially surprising. Why run Linux on million-dollar mainframes? But it made sense for consolidation. Running thousands of Linux virtual machines on one physical mainframe. IBM's advertising campaign was memorable. Television commercials featured a young boy representing Linux with adults representing IBM explaining how they'd support him. Print ads showed penguins, the Linux mascot, with slogans like "Peace, Love, Linux." The campaign brought Linux mainstream visibility. Oracle's Larry Ellison positioned Oracle Database on Linux aggressively. Oracle performed benchmarks showing Linux performance comparable to commercial Unix, sometimes superior. The company marketed Linux as a low-cost alternative to Solaris, HP UX, and AIX, conveniently systems from Oracle's competitors. Oracle's support was significant because databases were critical enterprise workloads. If databases ran well on Linux, many other applications could too. Oracle's certification removed a major objection to enterprise Linux adoption. Other database vendors followed. IBM DB2, Sybase, and smaller databases supported Linux. MySQL and PostgreSQL, open-source databases, ran natively on Linux and gained popularity for web applications. In 2003, Munich announced plans to migrate approximately 14,000 desktop computers from Windows to Linux. This decision generated international attention as one of the largest desktop Linux deployments attempted. Munich's motivations included cost savings from eliminating Microsoft licensing fees, greater independence from vendor lock-in, supporting open standards, philosophical preference for free software. The project, called LiMux, took years longer than initially planned and cost more than expected. Technical challenges included application compatibility, user training, and hardware support. Political challenges involved Microsoft lobbying to prevent the migration. LiMux became symbolic of desktop Linux possibilities and challenges. Proponents cited it as proof Linux could replace Windows for government use. Critics pointed to delays and difficulties as evidence Linux wasn't ready for desktop deployment. The project continued into the 2010s, though Munich eventually decided to return to Windows in 2017, later reversed again in 2020, illustrating persistent desktop Linux challenges. In March 2003, SCO Group, formerly Caldera, filed a lawsuit against IBM claiming Linux contained Unix source code owned by SCO. SCO claimed IBM had improperly contributed AIX, IBM's Unix code to Linux, violating SCO's Unix licensing agreements. SCO sent letters to Linux users claiming they needed SCO licenses to legally run Linux. The The company demanded hundreds of thousands of dollars per CPU. This created fear, uncertainty, and doubt, FUD, about Linux's legal status. The Linux community and IBM fought back aggressively. IBM countersued, claiming SCO violated GPL and IBM copyrights. Legal experts analyzed SCO's claims, finding them weak. The community rallied to defend Linux's legitimacy. Gradual, a website founded by Pamela Jones, meticulously documented the case, explaining legal proceedings and analyzing SCO's claims. Gradual became crucial for community understanding and organizing defense. The lawsuit dragged on for years through various courts. SCO filed for bankruptcy in 2007, but litigation continued. Eventually, courts ruled against SCO on most claims. In 2010, the court ruled SCO didn't own the Unix copyrights it claimed, undermining its entire case. The SCO lawsuit ultimately failed, but consumed significant resources and created uncertainty during critical years. It highlighted intellectual property concerns around open-source software. The Linux community emerged stronger, having successfully defended against legal threats. But the episode demonstrated that legal challenges could threaten open-source projects. Linux 2.6, released in December 2003, brought revolutionary changes. This kernel version would remain the stable branch for years, receiving continuous updates rather than a new major version. Key improvements included new O1, scheduler constant time task scheduling regardless of process count, improving performance under load, NPTL, native POSIX thread library, vastly improved threading performance, crucial for modern multi-threaded applications, better SMP scalability, support for systems with hundreds of processors, improved I/O performance, new I/O schedulers optimized for different workloads, CFQ, deadline, NUP, better hardware support, improved drivers for graphics cards, wireless networking, USB devices, and more. Improved power management, better laptop support with CPU frequency scaling and advanced power management. Enhanced security, SoLinux, security enhanced Linux integration providing mandatory access controls. Better file systems, improvements to XT3, support for XFS, Riser FS enhancements. The 2.6 kernel architecture proved remarkably adaptable. Rather than freezing and starting a 2.7 development cycle, the kernel team continued evolving 2.6 through minor version updates, 2.6.1, 2.6.2, etc. This approach maintained stability while incorporating innovations. The kernel development process formalized. Andrew Morton became Linus Torvalds' primary lieutenant, managing the memory management tree where patches were tested before mainline inclusion. Subsystem maintainers manage specific kernel areas. This hierarchical structure scaled to handle thousands of contributors. GNOME and KDE, the two major desktop environments, competed vigorously. Each had distinct philosophies and technical approaches. GNOME, started in 1997 by Miguel de Casa and Federico Mena, GNOME emphasized simplicity, usability, and complete freedom, avoiding Qt's initial licensing restrictions. Based on GTK+, GNOME aimed for a clean, uncluttered interface. Red Hat and Debian favored GNOME. KDE, started in 1996 by Matthias Ettrich. KDE emphasized power and configurability. Based on Qt, later GPL licensed, KDE provided extensive customization options and integrated applications. SysOSE and Mandrake favored KDE. This competition benefited users through innovation, but also fragmented effort. Applications often worked better in their native environment. Different toolkits, GTK+ versus Qt, meant applications looked inconsistent. Debates about which environment was better consumed community energy. Both environments matured significantly during this period. GNOME 2.x, released in 2002, provided a polished, stable desktop. KDE 3.x, released in 2002, offered powerful features and attractive visuals. Linux desktops were becoming genuinely usable, though still primarily for technical users. In October 2004, Mark Shuttleworth announced Ubuntu Linux. Shuttleworth, a South African entrepreneur who had made hundreds of millions from Thought, a digital certificate company, founded Canonical Lead Aid to develop Ubuntu. Ubuntu distinguished itself through ease of use, focus on working out of the box with minimal configuration, regular releases, predictable 6-month release cycle, April and October, live CD, ability to try Ubuntu without installing, reducing barriers, free shipping. Canonical initially shipped free CDs worldwide, remarkable for distribution, professional presentation, polished branding and design, not typical of Linux distributions. Debian Base, built on Debian providing stability and extensive package repositories. Ubuntu's slogan, Linux for Human Beings, acknowledged Linux's reputation for being difficult. The distribution targeted normal users, not just system administrators and programmers. Ubuntu quickly gained popularity, particularly among users new to Linux. Its timing was fortunate. Hardware support had improved, desktop environments had matured, and Firefox provided a quality web browser. Ubuntu assembled these pieces into a coherent, accessible system. The Ubuntu community grew rapidly. Forums provided support. Derivative distributions emerged, Kubuntu with KDE, Xubuntu with XFCE, etc. Ubuntu became the most popular desktop Linux distribution, introducing many people to Linux. However, Ubuntu's commercial backing and decisions sometimes created friction with the broader community. Canonical's influence over Ubuntu's direction, its addition of Amazon search integration, and later decisions like Unity Desktop and Snap packages generated controversy. The mid-2000s saw the Web 2.0 revolution, dynamic user-generated content replacing static web pages. Social networks, blogs, wikis, and web applications proliferated. Linux and the LAMP stack powered most of this growth. Companies building web services overwhelmingly chose Linux. Google built its entire infrastructure on modified Linux. Facebook ran on LAMP, later heavily customized. Wikipedia ran on Linux, Apache, and MySQL. Twitter initially ran on Ruby, on Rails, on Linux. Amazon Web Services was built on Linux. Linux's dominance in web infrastructure wasn't accidental. The LAMP stack provided zero licensing costs, critical for startups with limited capital. Flexibility. Open source enabled customization for specific needs. Performance. Linux and Apache handled web workloads efficiently. Stability. Linux systems ran for months or years without rebooting. Scalability. Horizontal scaling across many Linux servers was straightforward. As web companies succeeded, Linux succeeded. Google's growth meant thousands of Linux servers. Facebook's expansion meant more Linux deployment. The web's infrastructure was fundamentally Linux-based. Virtualization transformed server computing, with Linux central to this transformation. Multiple virtualization technologies emerged. Zen, an open-source hypervisor developed at Cambridge University. Zen enabled running multiple operating systems simultaneously. Zen used paravirtualization, guest OS modified for virtualization, and later hardware virtualization, CPU support for virtualization. Amazon Web Services initially used Zen for EC2, Elastic Compute Cloud, VMware, commercial virtualization leader. VMware supported Linux guests well and later Linux hosts. VMware's success demonstrated virtualization's value, increasing Linux deployment as guests. KVM kernel-based virtual machine merged into the Linux kernel in 2007. KVM turned Linux into a hypervisor using hardware virtualization support. KVM's integration with Linux made virtualization a native kernel feature. Virtualization enabled server consolidation, multiple virtual machines on one physical server, improving utilization, flexible resource allocation, easy to provision and resize virtual machines. Rapid deployment, creating new virtual machines took minutes, not days. Disaster recovery. Virtual machines could be backed up, replicated, and migrated. Linux benefited from virtualization both as host and guest. As host, Linux with KVM provided excellent virtualization performance. As guest, Linux ran on VMware, Zen, and other hypervisors efficiently. Cloud computing built on virtualization made Linux even more dominant. Amazon Web Services, launched in 2006, primarily supported Linux. Most cloud virtual machines ran Linux because it was efficient, free, and well-suited for server workloads. In 2007, the Free Standards Group and the Open Source Development Labs merged to form the Linux Foundation. This organization provided neutral governance for Linux and related projects. The Linux Foundation's roles included employing Linus Torvalds, ensuring he could work full-time on kernel development without vendor dependence, coordinating development, hosting infrastructure, organizing conferences, facilitating collaboration, legal protection, providing legal resources to defend Linux against threats, standardization, developing standards like the Linux Standard Base, promoting Linux, marketing, and educating about Linux. The Foundation's funding came from corporate members at various membership levels: Platinum, Gold, Silver. Major technology companies joined, demonstrating Linux's commercial importance. Membership fees supported Linux development and promotion. The Linux Foundation represented Linux's institutional maturity. What began as one student's hobby project now had professional organization, significant funding, and support from the world's largest technology companies. In 2005, a crisis emerged in kernel development. BitKeeper, the proprietary version control system used for kernel development, revoked free licenses for Linux developers. This decision, following tensions over reverse engineering attempts, left kernel development without version control. Linus Torvalds decided to create a new version control system rather than adopt existing alternatives like CVS or Subversion, which he considered inadequate. In April 2005, Torvalds began coding Git, British slang, meaning unpleasant person. Torvalds' self-deprecating humor. Git's design reflected kernel development needs. Distributed. Every developer has complete repository history, not dependent on central servers. Performance. Optimized for speed. Handling kernel-sized repositories efficiently. Branching. Easy branching and merging, supporting experimental development. Integrity. Cryptographic integrity checking, preventing corruption. Non-linear development, supporting complex workflows with multiple branches. Torvalds developed Git's core functionality in weeks, demonstrating his programming skill. The kernel project switched to Git by June 2005. Junio Hamano became Git's maintainer, allowing Torvalds to return to kernel development. Git's influence extended far beyond the kernel. It became the dominant version control system for open source projects and increasingly for commercial development. GitHub, founded in 2008, built a platform around Git that revolutionized collaborative software development. By the 2010s, Git was the standard, displacing older systems like CVS and Subversion. In 2007, Google announced Android, a mobile operating system for smartphones. Android was based on the Linux kernel, but diverged significantly from typical Linux distributions. Android's architecture included Linux kernel, provided core OS functionality, hardware abstraction, drivers, Android runtime, Java-based application environment, initially Dalvik VM, later ART, Android framework, APIs for application development, Android applications, Google Apps, and third-party applications. Android wasn't Linux in the traditional sense. It didn't use GNU tools, X Windows, or standard Linux desktop components. The kernel was modified extensively for mobile needs, power management, security features, and mobile-specific hardware. The first Android phone, the T-Mobile G1, HTC Dream, launched in October 2008. Initially, Android competed against Apple's iPhone, launched 2007, BlackBerry, and Windows Mobile. Android's growth was exponential. By device count, Android made Linux the world's most used operating system. Hundreds of millions, then billions of Android devices were sold. Most users didn't realize they were running Linux. Android's branding didn't emphasize its Linux heritage. Android's relationship with the Linux community was complex. Google contributed many patches to the mainline kernel, but some Android-specific code remained separate. Tensions existed over this divergence, though over time, more Android code merged into the mainline kernel. Android demonstrated Linux's versatility. The same kernel running on supercomputers and servers also powered pocket-sized smartphones. This portability vindicated Linux's design philosophy. The 2008 financial crisis and subsequent recession paradoxically benefited Linux. Organizations sought cost savings, and Linux's zero licensing cost became even more attractive. Companies accelerated migration from proprietary Unix, Solaris, HP UX, AIX, to Linux. While commercial Unix systems were powerful, their licensing costs were substantial. Linux provided comparable functionality at far lower cost. Hardware vendors like Sun Microsystems and HP saw Unix revenue decline as Linux captured market share. Windows to Linux migration also increased, though primarily on servers. Desktop Windows remained dominant, but Linux gained server market share from Windows, especially for web servers and infrastructure services. The recession also affected Linux companies. Red Hat navigated successfully, continuing revenue growth, but smaller vendors struggled. The crisis forced focus on sustainable business models rather than dot-com-era speculation. Linux's supercomputing dominance became overwhelming during this period. The top 500 list ranking the world's fastest supercomputers showed increasing Linux prevalence. 2005, 72% of top 500 systems ran Linux. 2007, 85% ran Linux. 2010, 91% ran Linux. By 2017, all 500 systems on the top 500 list ran Linux. Linux's supercomputing dominance resulted from several factors. Customizability. Supercomputers are unique, requiring customized software. Linux's open source enabled this. Cost. Supercomputers cost millions. Eliminating OS licensing saved substantially. Performance. Linux's efficiency and ability to eliminate unnecessary services maximized performance. Community. Academic and research institutions drove supercomputing and preferred open systems. Supercomputing Linux distributions were highly specialized. Custom kernels, optimized libraries, and unique configurations were standard. This flexibility was impossible with proprietary operating systems. Linux proliferated in embedded systems during this period. Devices containing Linux included consumer electronics, TVs, set-top boxes, digital video recorders, networking equipment, routers, switches, wireless access points, automotive, in-vehicle infotainment systems, navigation, industrial control, manufacturing equipment, robotics, medical devices, various medical equipment, aerospace, avionics, and spacecraft systems. Linux's advantages for embedded systems included no licensing costs, important for high-volume consumer products, flexibility, extensive customization for specific hardware and needs, available drivers, wide hardware support, reduced development time, maturity, stable, well-tested code base, community support, resources, and expertise readily available. Many embedded systems used BusyBox, a single executable containing tiny versions of many common Unix utilities, minimizing footprint. Embedded Linux distributions like OpenWrt for routers, BuildRoot, and Yocto project facilitated development. Most consumers never knew their devices ran Linux. A TiVo or wireless router didn't advertise powered by Linux, but millions of such devices ran Linux internally. By 2010, Linux kernel development reached extraordinary velocity. Statistics from the Linux Foundation showed just 10,000 lines of code added daily to the kernel, contributions from 1,000 plus developers per kernel release, representing 200 plus companies, new kernel releases every 2-3 months. Major corporate contributors included Intel, Red Hat, Novell, IBM, Texas Instruments, Nokia, Samsung, Google, and many others. The corporate involvement was massive. Over 75% of kernel contributions came from paid developers. Yet the development process remained remarkably open and meritocratic. Anyone could contribute patches. Linus Torvalds and subsystem maintainers reviewed code on technical merit, not contributor status. This combination of corporate resources and open processes proved extraordinarily effective. The kernel surpassed 13 million lines of code. Despite its size, quality remained high. Serious bugs occurred, but were usually fixed rapidly. The development model that skeptics once questioned had proven itself beyond doubt. Cloud computing fundamentally transformed enterprise IT with Linux as its bedrock. The major cloud providers all built infrastructure primarily on Linux. Amazon Web Services, AWS, the dominant cloud provider, ran on Linux. EC2, Elastic Compute Cloud primarily offered Linux virtual machines. AWS services like S3, storage, RDS, databases, and Lambda, serverless computing, all ran on Linux infrastructure. Google Cloud Platform, Google's infrastructure built on custom Linux distributions, formed the basis of its cloud offerings. Google had used Linux internally for years, and cloud services continued this approach. Microsoft Azure, remarkably. Even Microsoft's cloud increasingly supported and ran Linux. Initially Windows-centric, Azure expanded Linux support as customers demanded it. By 2016, Microsoft acknowledged that approximately 1/3 of Azure virtual machines ran Linux, a percentage that continued growing. Microsoft's transformation from Linux opponent to supporter was dramatic. OpenStack. This open-source cloud computing platform used by many private clouds was built on and primarily ran Linux. Cloud computing's economic model, pay for resources used, made Linux's zero licensing cost even more advantageous. Cloud providers could provision thousands of Linux virtual machines without per-instance licensing fees. This cost structure was passed to customers through lower prices. In July 2011, Linux 3.0 was released. The version number jump from 2.6.39 to 3.0 was primarily cosmetic, marking 20 years since the original Linux release. Torvalds acknowledged that version numbers had become unwieldy and simplified the scheme. The 3.x kernel series continued rapid development. Improvements included better power management, crucial for laptops and mobile devices, improved file systems, BTRFS maturation, XT4 enhancements, enhanced graphics support, better drivers for AMD, Intel, and NVIDIA GPUs, improved security, additional security modules and hardening, better ARM support, as ARM processors became more important in servers and devices. The kernel development process continued evolving. The release cycle stabilized at approximately 9 to 10 weeks. Stable kernel maintenance improved, with long-term support kernels receiving updates for years. In March 2013, Docker was released, revolutionizing application deployment. While Linux containers had existed for years using kernel features like namespaces and C groups, Docker made containers accessible and practical. Docker provided simple interface, easy commands for building, shipping, and running containers. Dockerfile, declarative format for defining container images. Docker Hub, registry for sharing container images. Layered images, efficient storage and sharing of container images. Portability, containers run consistently across different environments. Docker's impact was immediate and transformative. Developers could package applications with all dependencies, eliminating works on my machine problems. Containers were lighter weight than virtual machines, starting in seconds rather than minutes. Microservices architectures became practical, with applications split into multiple containerized services. The container ecosystem expanded rapidly. Orchestration tools emerged to manage container clusters. Google developed Kubernetes, released as open source in 2014, which became the standard container orchestration platform. Kubernetes automated deployment, scaling, and management of containerized applications. Containers ran on Linux, initially exclusively, though Windows containers later emerged. Container adoption drove further Linux deployment, particularly in cloud environments. Companies standardized on containerized deployments, typically on Linux hosts. In 2012, Red Hat achieved a significant milestone, over $1 billion in annual revenue. This was the first open-source company to exceed this threshold, demonstrating that open-source business models could generate substantial revenue. Red Hat's success came through Enterprise Linux support. Red Hat Enterprise Linux RHL provided stable, supported Linux for enterprises, middleware, and applications. JBoss, OpenShift, Container Platform, and other products. Subscriptions. Annual subscription model provided recurring revenue, training and consulting, services around Linux deployment and management. Red Hat's model, give away software but charge for support, services, and enterprise features, proved sustainable. The company competed successfully against proprietary software vendors while maintaining open-source principles. Other Linux companies had varying success. Canonical, Ubuntu, received investments but struggled with profitability. SUSE changed ownership multiple times. Community distributions like Debian and Arch continued thriving without commercial sponsorship. Red Hat's success validated open source commercially. It demonstrated that companies could build valuable businesses around free software, addressing long-standing questions about open source sustainability. Google launched Chromebooks in 2011, running Chrome OS, based on the Linux kernel. Chromebooks were designed as web-centric devices, running applications primarily in the Chrome browser. Chrome OS's architecture included Linux kernel, customized for security and performance, Chrome browser, primary application interface, web applications, Gmail, Google Docs, and other web apps. Android app support, added later, enabling mobile apps on Chromebooks. Initially dismissed as too limited, Chromebooks found success in education. Schools appreciated their low cost, easy management, and security. By the mid-2010s, Chromebooks outsold Macs in U.S. education. Chromebooks demonstrated that Linux could succeed on consumer devices with the right approach. Users didn't know or care about the underlying OS. They wanted devices that worked simply and securely. Chrome OS provided this while running on Linux. Systemed, an init system and service manager, generated intense controversy when major distributions adopted it. Lennart Poettering and K. Sievers developed System to replace traditional sysv init. System provided parallel service startup, faster boot times through parallel initialization, dependency-based startup, services start when dependencies are met, on-demand service activation, services start only when needed, unified management, single tool, systems for service management, extensive features, logging, journaled, network management, and much more. Systems advantages were clear: faster boot times, better dependency handling, and modern features. Major distributions adopted it: Fedora 2011, Arch 2012, Ubuntu 2015, Debian 2015. However, System generated fierce opposition. Complexity: System was large and complex, violating Unix philosophy of simple focused tools. Scope creep: System absorbed functionality beyond init, logging, networking, etc. Binary logs: System used binary log files, not text, complicating troubleshooting. Forced adoption: once adopted by distributions, System was difficult to avoid. The controversy split the community. Some distributions explicitly rejected System. Debian forked from Debian to avoid System. Debates became bitter, sometimes personal. Despite controversy, System adoption continued. Its practical advantages outweighed philosophical objections for most distributions. By 2015, System was standard on major distributions, though debate continued. As Linux became more important, security received increased attention. Several major vulnerabilities were discovered. Heartbleed 2014, a critical vulnerability in OpenSSL, widely used for encrypted communications. While not Linux-specific, it affected millions of Linux servers. The bug had existed for years, demonstrating that open source didn't automatically mean secure. Shellshock 2014, a vulnerability in Bash, the standard Linux shell, allowing arbitrary code execution. Decades old, the bug affected countless systems. Dirty Cow 2016, a Linux kernel privilege escalation vulnerability existing since 2007. These vulnerabilities prompted introspection. How could serious bugs persist for years in widely used open source software? Responses included increased funding. The Linux Foundation created the Core Infrastructure Initiative to fund security audits of critical open-source projects, better code review, enhanced scrutiny of patches and code changes, security hardening, kernel features like address space, layout randomization, ASLR, DEP, data execution prevention, and security modules improved, fuzzing, automated testing to discover vulnerabilities. Linux security matured significantly. Security-focused distributions like SE Linux, Security Enhanced Linux, and AppArmor provided mandatory access controls. Secure boot support improved. Container security received attention as containers proliferated. However, security remained ongoing work, not a solved problem. New vulnerabilities continued emerging, requiring constant vigilance. The Internet of Things, IoT, billions of connected devices relied heavily on Linux. Smart home devices, industrial sensors, wearables, and countless other IoT devices ran embedded Linux. Linux's IoT advantages included minimal footprint. Linux could run on resource-constrained devices, connectivity, excellent networking support, flexibility, customizable for specific device needs, no licensing costs, critical for high-volume consumer devices. However, IoT also presented challenges. Security. Many IoT devices had poor security, being compromised for botnets. Mirai Botnet demonstrated this dramatically in 2016. Fragmentation. Thousands of customized Linux versions made unified security updates difficult. Outdated software. Devices often ran old, unpatched Linux versions. Edge computing, processing data near where it's generated rather than in centralized clouds, grew alongside IoT. Edge computing used Linux extensively, with custom distributions optimized for edge deployments. Desktop Linux made gradual progress during this period. Distributions improved significantly. Ubuntu matured as the leading desktop Linux, though Unity desktop interface proved controversial. Linux Mint gained popularity as a user-friendly Ubuntu derivative. Fedora provided cutting-edge features for developers and enthusiasts. Elementary OS focused on design and user experience. Desktop environments evolved. GNOME 3 radical redesign in 2011 proved controversial but matured over time. KDE Plasma 5 released in 2014, continuing KDE's tradition of feature-rich configurability. XFCE, LXDE, and others. Lightweight alternatives for older hardware. Gaming on Linux improved significantly. Steam for Linux. Valve released Steam Client for Linux in 2013. More native games. Developers increasingly supported Linux. Wine improvements. Windows compatibility layer improved. Graphics driver progress. Proprietary and open-source graphics drivers improved. Despite progress, desktop Linux market share remained around 1–2% globally. Windows and Mac OS dominated. Challenges included application availability. Many popular applications didn't support Linux. Hardware support. Some hardware, particularly laptops, had inconsistent Linux support. Fragmentation. Multiple distributions and desktop environments created fragmentation. Corporate support. Lack of corporate backing for desktop Linux, unlike server Linux. Yet desktop Linux sustained a dedicated community. Developers, system administrators, and enthusiasts used it successfully. For certain workflows, particularly programming and system administration, Linux was excellent. Microsoft's transformation regarding Linux was remarkable. The company that called Linux a cancer in 2001 dramatically changed course. Windows Subsystem for Linux, WSL. Announced in 2016, WSL allowed running Linux distributions directly on Windows. This wasn't virtualization. WSL provided a Linux-compatible kernel interface on Windows, enabling native Linux binary execution. USL2 2019 used a real Linux kernel for better compatibility. Linux Foundation membership. In 2016, Microsoft joined the Linux Foundation as a platinum member, contributing hundreds of thousands of dollars annually. Azure Linux support. Microsoft embraced Linux on Azure, with the majority of Azure virtual machines running Linux by the late 2010s. Open source contributions. Microsoft became a major open source contributor, releasing projects like Visual Studio Code, TypeScript, and .NET Core as open source. This transformation reflected business reality. Customers wanted Linux, particularly in cloud environments. Fighting Linux was counterproductive. Embracing it made strategic sense. Satya Nadella, who became Microsoft's CEO in 2014, drove this cultural shift with his mantra, "Microsoft loves Linux." The Microsoft embrace generated mixed reactions in the Linux community. Some welcomed cooperation, others remained skeptical, remembering past antagonism. The phrase, "embrace, extend, extinguish," describing a historical Microsoft strategy, was invoked warily. Kubernetes, initially developed by Google and released as open source in 2014, became the dominant container orchestration platform by 2016-2017. The Cloud Native Computing Foundation, CNCF, part of the Linux Foundation, stewarded Kubernetes development. Kubernetes provided container orchestration, automated deployment, scaling, and management of containers, service discovery and load balancing, automatic networking between services, self-healing, automatic restarting of failed containers, rolling updates, update applications without downtime, secrets and configuration management, secure handling of sensitive data. Kubernetes revolutionized application deployment. Companies standardized on Kubernetes for running applications, both on-premises and in clouds. Major cloud providers offered managed Kubernetes services: Amazon EKS, Google GKE, Azure AKS. The cloud-native approach, designing applications specifically for cloud environments, became standard. Cloud-native architectures typically involved microservices, applications split into small, independent services, containers, services packaged as containers, Kubernetes, orchestration and management, DevOps practices, automated deployment, and continuous integration saw our delivery. Linux, almost exclusively running on Linux hosts. Kubernetes drove further Linux adoption. Organizations deploying Kubernetes almost always used Linux for the underlying infrastructure. The platform's dominance made Linux increasingly the default choice for modern application deployment. The CNCF ecosystem expanded beyond Kubernetes to include numerous projects: Prometheus, monitoring, Envoy, networking, containered, container runtime, Helm, package management, and dozens more. This ecosystem, built on and for Linux, represented the future of infrastructure software. The Linux kernel continued evolving through the 4.x series 2015-2019 and into 5.x 2019 present. Major developments included improved security features, kernel lockdown mode preventing even root from modifying the running kernel, better speculative execution attack mitigations, Spectre Meltdown patches, enhanced seccomp, secure computing mode for sandboxing, improved address space isolation, performance improvements, better multi-core scaling for massive processor counts, improved memory management and page allocation, better I/O performance with I/O urine, asynchronous I/O interface, CPU scheduler improvements, EAS for energy-aware scheduling, file system advances, BTRFS maturation with better reliability, F2FS optimization for flash storage, XT4 continued improvements, XFS scalability enhancements, hardware support, better laptop and mobile device support, improved graphics drivers, AMD contributions, Intel improvements, support for new CPU features and architectures, better power management for battery-powered devices, architecture expansion. ARM64 became increasingly important as RMA processors entered servers. RISC-V support for the emerging open-source processor architecture, continued support for dozens of other architectures. The kernel exceeded 20 million lines of code by 2017 and 30 million by 2020. Despite this growth, quality remained high due to rigorous testing and code review processes. Development velocity remained extraordinary. The Linux Foundation's annual kernel development reports showed over 10,000 changes per release every 9 to 10 weeks. Contributions from 1,500 to 2,000 developers per release, representing 200-300 companies. About 100,000 lines added, 60,000 removed, and 100,000 modified per release. Corporate involvement remained massive. Top contributing companies included Intel, Red Hat, Linaro, IBM, Samsung, SUSE, Google, AMD, Renesas, Mellanox, and many others. Individual volunteers still contributed significantly, but corporate-backed developers dominated numerically. Gaming on Linux improved dramatically, largely due to Valve's investments. Valve, operator of the Steam gaming platform, had strategic reasons to support Linux, reducing dependence on Microsoft's Windows. In August 2018, Valve released Proton, a compatibility layer enabling Windows games to run on Linux. Built on Wine, Windows compatibility layer, and other technologies, Proton allowed thousands of Windows games to run on Linux with minimal modifications. Proton's impact was significant. Steam's Linux game library effectively expanded by thousands of titles. Games that publishers hadn't ported to Linux suddenly worked. While not all games worked perfectly, compatibility steadily improved. In July 2021, Valve announced the Steam Deck, a handheld gaming PC running Steam OS 3.0 based on Arch Linux. The Steam Deck shipped in early 2022 and became successful, selling millions of units. The Steam Deck demonstrated Linux's viability for consumer gaming. Most users didn't know or care that it ran Linux, they wanted to play games. The device worked reliably, providing excellent gaming experiences on Linux. Valve's efforts made Linux a genuine gaming platform. While Windows remained dominant for PC gaming, Linux became viable. Some game developers even began supporting Linux officially, recognizing the growing user base. In January 2018, major CPU vulnerabilities called Spectre and Meltdown were publicly disclosed. These vulnerabilities affected modern processors from Intel, AMD, and ARM, exploiting speculative execution, a performance optimization where CPUs execute instructions speculatively before knowing if they're needed. Spectre and Meltdown allowed attackers to read arbitrary memory, potentially exposing passwords, encryption keys, and sensitive data. The vulnerabilities existed in hardware, not software, making them particularly serious. Linux kernel developers worked frantically to develop mitigations. The KPTI, Kernel Page Table Isolation, patch helped mitigate Meltdown by isolating kernel memory more strictly. Spectre mitigations were more complex, requiring various techniques to prevent exploitation. The mitigations carried performance costs. Some workloads slowed by 5 to 30%. This created dilemmas: security versus performance. Different organizations made different trade-offs based on their security requirements and performance needs. The incident demonstrated challenges in securing complex modern systems. Hardware bugs could undermine software security. It also showcased the Linux community's ability to respond rapidly to serious threats. Comprehensive mitigations were developed and deployed within weeks. ARM processors, traditionally used in mobile devices and embedded systems, began entering servers and even desktops. ARM's power efficiency made it attractive for data centers concerned about energy costs. Several developments drove ARM server adoption: specialized processors. Amazon designed Graviton processors, ARM-based, for AWS. These provided excellent price performance for certain workloads. Software ecosystem: Linux's excellent ARM support made ARM servers practical. Most server software ran on ARM Linux with minimal modifications. Price performance: ARM processors sometimes offered better performance per dollar or per watt than x86. Apple's transition to ARM-based Apple Silicon for Macs 2020 was significant. While Macs ran Mac OS, not Linux, the transition validated ARM for desktop and laptop computing. Some projects brought Linux to Apple's Silicon hardware. NVIDIA's attempted acquisition of ARM, announced 2020. Abandoned 2022 due to regulatory concerns, demonstrated ARM's strategic importance. The acquisition would have given NVIDIA control over processor designs, licensing to hundreds of companies. Linux's ARM support was crucial for ARM server adoption. Because Linux ran well on ARM and most server software ran on Linux, porting server applications to ARM was relatively straightforward. This portability demonstrated Linux's design philosophy's value. In 2021, a significant debate emerged about incorporating Rust, a modern programming language emphasizing safety and performance, into the Linux kernel. Rust's memory safety guarantees could prevent entire classes of bugs, use after free, buffer overflows, etc. that plague C code. Miguel Ojeda led efforts to enable Rust development in the Linux kernel. This was controversial. Proponents argued memory safety would prevent serious security vulnerabilities. Modern language features would improve productivity. Attracting Rust developers would expand contributor base. Gradual adoption could occur without disrupting existing code. Skeptics worried. Adding another language increased complexity. C worked fine. Why change? Rust's stability and longevity were unproven for kernel work, build system complications and dependencies. In December 2021, Linus Torvalds indicated openness to Rust in the kernel, though he emphasized any adoption would be gradual and practical. In October 2022, Linux 6.1 included preliminary Rust infrastructure support, allowing Rust code, initially just for drivers, to be compiled into the kernel. This represented potential major evolution for Linux. The kernel had been exclusively C and assembly for over 30 years. Adding another language was historically significant, though full Rust adoption would take years, if it occurred at all. Linux's reach extended to extraordinary environments. NASA's Mars helicopter Ingenuity, which flew on Mars in 2021, ran Linux. The International Space Station used Linux for various systems. SpaceX's Falcon, Affine 9 rockets, and Dragon spacecraft used Linux. Linux's space adoption reflected its reliability, flexibility, and customizability. Space missions require robust software that can be modified for specific needs. Linux provided this. The ability to fix bugs and add features without vendor dependence was crucial for long-duration missions. Beyond space, Linux ran in extreme environments. Submarines. Nuclear submarines used Linux for various systems. Particle accelerators. The Large Hadron Collider at CERN used Linux extensively. Automotive. Modern vehicles increasingly ran Linux-based infotainment and control systems. Industrial control, manufacturing, power plants, and infrastructure used embedded Linux. This ubiquity demonstrated Linux's maturity and versatility. The system could handle everything from smartphones to spacecraft, from wearables to supercomputers. Desktop Linux market share remained around 2–3% globally through the 2010s and into the 2020s, depending on measurement methodology. While small, this represented millions of users. Progress occurred in several areas. Hardware support. Laptop support improved dramatically. Most hardware worked out of box on major distributions. Graphics drivers improved, particularly open-source AMD drivers. Software availability. More applications supported Linux. Web applications reduced dependence on native software. Electron enabled cross-platform applications. Usability distributions became more polished. Installation and configuration simplified. Desktop environments matured. Gaming. As discussed, Proton and Steam Deck transformed Linux gaming. However, challenges persisted. Professional applications, Adobe Creative Suite, Microsoft Office, and many professional applications didn't run on Linux. Corporate support. Most companies standardized on Windows or Mac OS, not Linux. Fragmentation. Multiple distributions and desktop environments created fragmentation. Learning curve. Linux still required more technical knowledge than Windows or Mac OS for troubleshooting. Some argued desktop Linux's small market share didn't matter. Linux succeeded where it mattered: servers, cloud, embedded. Others believed desktop Linux's inability to capture significant market share indicated fundamental usability issues. Desktop Linux found niches: developers, system administrators, privacy-conscious users, and people running older hardware. It provided excellent platform for programming and technical work. For users comfortable with its quirks, Linux offered a powerful, customizable desktop environment. By the 2020s, Linux's dominance in many areas was overwhelming. Linux ran approximately 70–90% of web servers, depending on methodology. Cloud providers were Linux-dominated. 100% of the top 500 supercomputers ran Linux. Android, Linux-based, powered approximately 70% of smartphones globally. Billions of devices, billions of embedded devices ran Linux, though exact numbers were difficult to determine. AWS, Google Cloud, and Azure all primarily ran Linux infrastructure. Docker, Kubernetes, and containerized deployments ran almost exclusively on Linux. Around 2–3% market share globally, representing tens of millions of users. The Linux kernel contained over 30 million lines of code. Each kernel release included contributions from approximately 2,000 developers, representing 200–300 companies. Development velocity remained extraordinary, releases every 9 to 10 weeks with thousands of changes each. The Linux Foundation employed Linus Torvalds and other key developers, coordinated development, hosted infrastructure, and promoted Linux. Corporate membership included virtually every major technology company. Linux faces ongoing challenges. The kernel's 30+ million lines of code are difficult to understand comprehensively. Managing complexity is ongoing work. As threats evolve, maintaining security requires constant effort. Hardware vulnerabilities, supply chain attacks, and sophisticated exploits pose risks. Balancing corporate interests, community needs, and technical excellence requires careful governance. Some vendors still provide poor Linux support or keep specifications proprietary. Despite decades of effort, desktop Linux remains a niche. While diversity is valuable, fragmentation across distributions and desktop environments creates challenges. As computation moves closer to data sources, Linux is well-positioned due to its flexibility and efficiency. ML frameworks predominantly run on Linux. GPU computing for AI almost exclusively uses Linux. Self-driving cars and advanced automotive systems increasingly use Linux. Billions of additional connected devices will need operating systems. Linux is well-positioned. RISC-V and other emerging architectures will need OS support. Linux's portability advantages continue. As cloud-native computing evolves, Linux's central role will likely expand. From Linus Torvalds' August 1991 announcement, "Just a hobby won't be big and professional," to 2024's reality, where Linux powers most of the internet, all supercomputers, billions of mobile devices, and critical infrastructure worldwide. Linux's journey is extraordinary. Linux succeeded through technical excellence, community engagement, strategic licensing, fortunate timing, and remarkable leadership from Torvalds and thousands of contributors. It demonstrated that open collaborative development could produce world-class software, rivaling anything created by traditional corporations. The operating system evolved from 10,000 lines of code created by one person to over 30 million lines contributed by thousands of developers from hundreds of companies. From running on a single person's PC to running on billions of devices, from smartphones to supercomputers, from hobbyist projects to strategic assets worth billions of dollars, Linux's transformation is unprecedented in software history. Challenges remain. Security requires constant vigilance. Managing complexity is ongoing work. Desktop adoption lags server success, but Linux's fundamental health is excellent. Development continues vigorously. Adoption expands continuously. The ecosystem thrives. Looking forward, Linux appears positioned for continued success. Cloud computing, AI, ML, edge computing, IoT, and automotive systems all trend toward greater Linux usage. Emerging technologies generally choose Linux as their platform. Perhaps most remarkably, Linux maintains its original character. Despite enormous commercial importance, development remains open. Anyone can contribute. Code review is meritocratic. The GPL ensures contributions remain free. Linus Torvalds still reviews patches and manages releases, though with more help than in 1991. Linux proves that idealism and pragmatism can coexist. Free software can power commercial success. Competition and collaboration aren't mutually exclusive. Individual initiative and community effort can combine powerfully. The penguin that symbolizes Linux, friendly, adaptable, thriving in harsh environments, aptly represents the operating system. Linux adapted to countless use cases, thrived despite corporate opposition, and succeeded through community effort. 30+ years after its creation, Linux isn't just successful, it's indispensable. Modern computing infrastructure would collapse without it. The internet, mobile communications, cloud computing, scientific research, and countless other domains depend on Linux. What began as one student's hobby project to understand task switching on a 386 processor became the foundation of 21st century computing. This transformation from just a hobby to global infrastructure represents not just technical achievement, but vindication of collaborative, open development's potential. Linux's history is still being written. New chapters involve AI, quantum computing, space exploration, and technologies not yet imagined. But the story's core remains unchanged. A community of talented, motivated people collaborating openly to build something remarkable. That story of human cooperation creating shared value is Linux's greatest legacy.